Two-port models for transistors. We've discussed the two-port model in a lecture video called Intro to Amplifiers. You should probably watch that one first before you watch this one. In this one, we're going to talk about the DC and the AC models that we use to represent the transistor itself. The DC model. So this is the one we use when there's constant current and constant voltage in the circuit, or DC currents and voltages. There's going to be two models talked about here, and they both have a dependent current source where the collector current is beta times IB. So that means that the current through this source right here, this is a dependent source, this current is beta times the base current. So the current that flows through here is beta times the current that comes in the base here. Both of these models have a dependent current source. The difference between these models is how we look at the input side. And on the input side here, current flows into the base and comes out the emitter. So in this first model, we think of this as the ideal diode on the base of the transistor. So we say that when current flows in here, we get 0 volts between the base and the emitter. This model can be used when Vn is high, and it's much higher than the 0.7 volts on the diode. Most of the time, we're going to use this model here, where current flows into the base, and it goes through the base emitter diode, and we get a 0.7 volt drop across it. This one should definitely be used when Vn is low, and when it's in about the same magnitude as the diode voltage. For the AC model, there's two common models. There's the T model and there's the pi model. In the T model, which is this one here, we have a dependent current source, and the current that goes from collector to emitter would be beta times IB. Now the T model, instead of a constant voltage drop on the input, we have an impedance which is called R'(E). This impedance is on the emitter. In the pi model, so that's this one here, it also has a dependent current source that allows current to flow from collector to emitter. But the impedance of the diode is over here, and it's called beta times R'(E). There's also a third model called the H parameter model, where it's called HIE, but it's in the same place as the pi model. It's over here. Although there's three names for these impedances, these three impedances are all the same thing. They represent a model of the same thing. And it's the impedance of the diode between the base and the emitter. The difference is where we consider it to be located. In the T model, we consider the impedance of the base emitter diode to be over here on the emitter side. But in the pi model and the H parameter model, we look at that impedance as being on the base side. So this is where we think that impedance is on the pi model and the H parameter model, and in the T model, we say that it's over here. And it represents the same thing in all of them. It's the diode impedance. It's the impedance of the diode between the base and the emitter. And it can be moved back and forth from the base to the emitter simply by multiplying or dividing by beta plus 1. So for example, in order to move the impedance from the emitter to the base, so here it is on the emitter, and if we want to move it over here on the base, what we need to do is we need to multiply it by beta plus 1. So take this, multiply it by beta plus 1, and then you've moved the impedance over to the base. If you want to move the impedance from the base to the emitter, so if it's over here and you want to move it over to the emitter side, what you would do is you would divide it by beta plus 1. This is done with a concept called reflected impedance, and it's explained in the Lab 5 notes, and I've also got a lecture video on that. Okay, so it's an impedance, and from where? Recall the base curve VB, the base curve for the diode. So this is the diode here between the base and the emitter, that when current flows in here, you get a 0.7 volt drop. So current flows in, you hit a 0.7 volt drop, and then current starts to increase rapidly. when we put current into the diode in this circuit here, we get a little bit of current going into the base. What will happen is that this circuit will reach a DC bias point, and in a DC circuit, then basically you will sit at one point on this diode curve. Let's say right here. And because it's constant current voltage, you're at one point. However, if you introduce a signal, if you put a signal into, apply a signal into the base here, then you're going to get the base current in VBE to change a little bit. It's going to vary between 2 points. So if you apply a signal, you're going to get IE and VBE to go back and forth between these 2 points. And what you can do is, so you'll have a delta V and a delta I between the 2 endpoints in this area. So let me just put those 2 points down. So basically, the current and the voltage is going back and forth between those 2 points, and we can draw a line between those 2 points that represents the slope of the line at that point. This slope is an impedance. It's a delta V over a delta I. And we can even put some numbers in it over here in an example. So let's say the base current varies between 1 and 2 milliamps, and VBE varies between 0.69 and 0.71 volts. So we could say that the impedance of that is a delta V over a delta I. It would be 20 millivolts. That's the difference here, 0.071 minus 0.69. So 20 millivolts over 1 milliamp would be 20 ohms. And if you've got these kind of values, you'd say that the impedance between the base and the emitter is 20 ohms. So in summary, we would estimate R prime E for the T model as being 25 millivolts over the DC emitter current. Now this 25 millivolts, this is something that is derived from Boltzmann's constant, and the current that you use is the DC emitter current when you solve the DC bias point. Now this formula seems like this 25 millivolts, well, it's a voltage over a current, which will give you an impedance. But this 25 millivolts and the fact that it's IE just kind of came out of nowhere. And in fact, in the text, he specifies that the formula for AC emitter resistance, that he could demonstrate that using solid state physics and calculus. So I'm going to say that's a little bit of a, you just have to take my word on it that this is possible. And if you want to learn more about it, you probably need to go on to physics or engineering at a university level, and maybe even do a master's or PhD study. So we'll just accept that the impedance on the base emitter diode is 25 millivolts divided by the DC emitter current. And that's the end of this one.